Welcome to the presentation with the title New Methods for Improving the Tribological Properties of Rolling Bearings, Triboconditioning. My name is Christoph Schirmer, and with the following presentation I would like to introduce you to the triboconditioning process in general and specifically to its application and potential in the context of rolling bearings. Now I will briefly present the agenda. First of all, I'll state the motivation of this presentation. Here I'll clarify the question of why tribological properties should be improved or optimized. Then I will discuss triboconditioning. This includes the basic idea of the process, the associated surface chemistry, that is, the chemical reactions that take place during the process, and the surface topography that results from the treatment. I will conclude this topic with the surface properties that result from triboconditioning. After that, I will discuss the potential of the process for rolling bearings and present a first experiment that the THWS conducted on tapered rollers. In the conclusion, I will summarize the main aspects of this presentation and give a short outlook on future topics concerning triboconditioning of rolling bearings. The energy transition and resource scarcity call for efficient and sustainable solutions. This obviously also applies to rolling bearings. One topic for achieving such solutions is the improvement or optimization of tribological properties. So what does this mean? Tribology consists of three fundamental areas: friction, wear, and lubrication. In the tribological optimization of rolling bearings, friction is to be reduced in order to minimize power losses. This results in better efficiency. Likewise, reduced wear leads to longer service lives of components and systems. For rolling bearings, in addition to improved geometries, materials, and lubricants, special treatment and coating processes can be used to improve tribological properties. Triboconditioning would compete with conventional processes like burnishing and coating. All these processes aim to improve tribological behavior, especially under deficient lubrication. On the left you can see a burnished rolling bearing. The surface contains various iron oxides, which improve the friction and wear behavior. In contrast to a friction and wear reducing coating and triboconditioning, burnishing additionally protects against corrosion. In the center you can see PVD coated rolling elements of a spherical roller bearing. This is a carbon coating which is very hard and reduces wear. On the right, triboconditioning is used for a camshaft. In contrast to the other two processes, triboconditioning has the advantage that it works in two ways. More on that later. Now I would like to present triboconditioning. Triboconditioning is a surface treatment method developed and patented by Tribonex, a small company from Sweden. In the left picture, the logo of the company is shown. The link tribonex.com, which can be found in the video description, takes you to the company's website. There you can find more information about triboconditioning as well as contact information. Triboconditioning is a protected trademark from Tribonex. The aim of this treatment is, as already mentioned, the improvement of tribological properties. The illustration on the right shows the principle of triboconditioning. A hard tool is drawn over a workpiece surface with high contact pressure under continuous feed of a special process fluid. This smooths the surface, and tribochemical interactions take place between the process fluid and the workpiece. The result is a plateau-like surface with a tribofilm, also called tribolayer, which contains an embedded solid lubricant. Triboconditioning can be implemented in two different process variants: triboconditioning round shape, which is used for round geometries, and triboconditioning complex geometry, which is used for complex geometries and small parts. For triboconditioning round shape, shown on the left, a honing tool, a pin, or a disc can be used. All tools have in common that they are made of carbide and that the process fluid is continuously fed. The honing tool can be used for internal geometries. It oscillates along the axis of the bore, while the workpiece or the tool perform a rotational movement. The pin can be used for external geometries. It performs a pivoting motion while the workpiece rotates. For a shaft shoulder, the disc is a suitable tool. In addition to surfaces parallel to the axis of rotation, the disc can reach shaft shoulders through face contact. For the treatment of rolling bearing raceways, it is possible to adapt standard tools to triboconditioning. Such standard tools can be grinding and honing tools from the rolling bearing industry. For triboconditioning complex geometry, shown on the right, basically all mass finishing processes can be used. An oil-based process fluid containing triboconditioning additives is used. The grinding media is high in density in order to generate a large impact. The preferred mass finishing processes for triboconditioning are centrifugal barrel finishing and stream finishing. In centrifugal barrel finishing, the revolver and the barrels are arranged eccentrically and rotated in opposite directions. The barrels contain several workpieces as well as the process fluid and process media. External surfaces can be easily treated with this process. For internal surfaces, the stream finishing process shown below is preferred. The workpieces are clamped on workpiece holders and immersed in a flow bath of process media and process fluid. In addition to this flow, the workpiece is rotated. Now I'd like to take a closer look at the surface chemistry. During triboconditioning, thermomechanical influences such as heat input, abrasion of oxide layers, and deformation provide for increased chemical reactivity. I will briefly introduce the reactions that are believed to occur during triboconditioning. The process fluid contains an organic sulfur complex RSR and tungsten trioxide WO3. Since iron is an important reactant to the reactions shown, the workpiece must be made of a ferrous material. In the first line, the organic sulfur complex from the process fluid decomposes as a result of friction, and a sulfidation of iron from the workpiece to iron sulfide FeS occurs. In the second line, the reduction of tungsten trioxide by iron forms a tungsten trioxide complex. The above-mentioned products react to tungsten disulfide WS2 and iron oxide FeO, as can be seen in line 3. Finally, the reactions are summarized in line 4. The tribochemical reactions shown are equilibrium reactions, occurring in regions of sufficient energy input. The tungsten disulfide represents the solid lubricant incorporated in the tribofilm. In the Auger electron microscopy of a triboconditioned shaft, shown on the right, small but relevant amounts of sulfur up to 120 nanometers are detectable. This corresponds to the thickness of the tribofilm. The surface topography is significantly changed as a result of triboconditioning. This is because material close to the surface is plasticized and made flowable. The peaks of the profile are smoothed and the valleys are partially filled. This results in a plateau-like surface. The figure shows the surfaces of a cylinder liner by means of secondary electron microscopy. The left figure shows the surface before triboconditioning, the right figure after triboconditioning. It can be clearly seen that most of the finer grooves are eliminated due to triboconditioning. However, larger grooves remain. Such a topography with plateau character influences the friction behavior favorably. The influences can be quantified via tactile roughness parameters and scattered light parameters. On this slide, I will present some tribologically meaningful tactile roughness parameters that change as a result of triboconditioning. First, I would like to briefly discuss the parameters from the material ratio curve, which is also called bearing area curve or Abbott-Firestone curve. On the right, you can see an exemplary roughness profile with the corresponding material ratio curve. By graphical construction in the material ratio curve, the reduced peak height RPK, the core roughness RK, and the reduced valley depth RVK can be derived. Triboconditioning reduces all three of the mentioned parameters. The reduction of RPK reduces wear, especially during running in. A lower RK value increases the contact area and therefore increases the load-bearing capacity. Reducing RVK slightly reduces lubricant retention. Now briefly to R delta Q. This parameter describes the root mean square value of the local slopes of a profile. Triboconditioning makes surfaces smoother, so the value decreases. This leads to easier lubricant film formation. RSK is the skewness of a profile, that is, the asymmetry of the amplitude density curve. The smaller or more negative this value is, the better the load-bearing capacity of the surface. Triboconditioning leads to a reduction of this parameter. The table below shows some tactile roughness parameter values on a cylinder liner. Here, conventional treatment is compared to triboconditioning. It is evident that the roughness values from the material ratio curve, as well as classic roughness values Rz and Ra, are reduced due to triboconditioning. Scattered light measurement is very suitable for the tribological characterization of a surface. First, I will introduce the principle of scattered light measurement using the illustration on the left. A measuring spot is generated on the sample by means of a LED light source. The light is then scattered back and directed via a measurement objective onto a photodiode detector array. The result is an intensity or frequency distribution of the scattered light over the scattering angle. The scattered light parameter AQ corresponds to the variance of the scattered light distribution. Because the scattering angles are evaluated, AQ is a measure of profile slopes. The lower the AQ value, the shallower the slopes of the profile are, meaning the surface is smoother. The figure on the right shows the results of a scattered light mapping on a cylinder liner. The surface before triboconditioning is shown at the top and after triboconditioning at the bottom. Before triboconditioning, the AQ values are between 20 and 30. After triboconditioning, AQ values between 10 and 20 are achieved. The AQ value is almost halved, which indicates significant smoothing. The influence of triboconditioning on the friction properties can be illustrated using a Striebeck curve. In the Striebeck curve, the coefficient of friction is on the y-axis with the Hersey number on the x-axis. The Hersey number is plotted logarithmically and is equal to the dynamic viscosity eta of the lubricant times the velocity v divided by the surface load p. The conventional treatment of a reference part is shown in red, a triboconditioned part is shown in blue, and a triboconditioned part using a low viscosity lubricating oil is shown in light blue with a dashed line. In the Striebeck curve you can see how triboconditioning improves the frictional properties. At low Hersey numbers in the dry friction regime, the solid lubricant tungsten disulfide reduces friction, C1. Furthermore, the range of mixed friction is shifted to the left towards higher loads and/or lower speeds, C2. This is due to the plateau-like surface that facilitates lubricant film formation. Optionally, triboconditioning allows the use of a low viscosity lubricant. Although this shifts the range of mixed friction somewhat to the right, the lubricated friction, that is the friction at higher Hersey numbers, decreases, C3. The wear of a triboconditioned surface is also reduced. There is low running-in wear and less fatigue damage because the smooth surface profile contains hardly any prominent profile peaks and has good load-bearing capacity. Furthermore, the tribofilm offers a certain resistance to cold welding. In the illustration, the influence of triboconditioning on wear is to be seen. The amount of wear over time is shown. A conventionally treated reference part is shown in red and a triboconditioned part in blue. As just described, the running-in wear of triboconditioned parts is lower. As a result, the amount of wear at the beginning of the so-called steady-state wear is lower than the one of the reference part. At a given tolerance level, this leads to a longer service life and increased functionality due to triboconditioning. During operation, wear of the tribofilm cannot be avoided. However, there is a self-regenerating effect due to tribochemical reactions between the surface and the lubricant, or rather its additives. Therefore, the reactants of triboconditioning must be matched to the lubricant in the subsequent application. Thus, unfavorable triboreactions associated with adverse changes in the properties of the surface can be avoided. An alternative for tungsten is molybdenium. Furthermore, sulfur can be substituted by phosphorus. In addition to friction and wear behavior, triboconditioning also improves surface integrity. The near-surface compaction leads to increased hardness and residual compressive stresses down to a depth of approximately 10 microns. In addition, grain refinement can potentially occur due to deformation and friction during triboconditioning. This would have a positive influence on strength, toughness, hardness, as well as tribological properties. For rolling bearings, triboconditioning is particularly relevant in the presence of temporary insufficient lubrication. The cause of insufficient lubrication in rolling bearings is poor friction conditions that prevent the formation of a load-bearing lubricant film. Such conditions exist, for example, during startup and shutdown of rolling bearings. In addition, low speeds paired with high loads can lead to insufficient lubricant film formation. In large bearings, the rolling elements are extremely accelerated when they enter the contact zone, which can tear the lubricant film open and thus also result in solid contact. This is referred to as slip in rolling bearings. The contacts between raceways and rolling elements are less frequently affected by insufficient lubrication than the secondary contacts. These secondary contacts include rib contacts, such as those found in cylindrical roller bearings and tapered roller bearings. Such a rib contact of a tapered roller bearing is shown on the right. Furthermore, cage contacts as well as rolling element contacts in full complement rolling bearings are susceptible to insufficient lubrication. On this slide, I would like to compare two rolling bearing finishing process chains. A conventional rolling bearing finish is shown in gray, and a rolling bearing finish that uses triboconditioning is shown in blue. In both process chains, the rolling bearing component is initially ground or hard turned. Here, the dimensions and the shape are adjusted. With conventional finishing, a honing or superfinishing follows in order to adjust the surface quality and cut roughness peaks. Then the component is burnished. Iron oxides are formed on the surface which improve the tribological behavior and have a passivating effect. With triboconditioning, the last mentioned processes of superfinishing and burnishing can be combined in one. Like superfinishing, triboconditioning improves the surface quality, and like burnishing, triboconditioning changes the surface composition by incorporating iron oxide FeO. In addition, a solid lubricant such as tungsten disulfide is produced. Adapted standard tools and mass finishing processes can be used to apply triboconditioning to rolling bearing components. The only requirement is that the components must be made of a ferrous material, for example steel or cast iron. To investigate the effects of triboconditioning on tapered rollers, an experiment was carried out. The subject of the investigation were 10 tapered rollers from a passenger car wheel bearing. 5 of these tapered rollers were left in the standard, that is, honed condition. The other 5 tapered rollers were additionally triboconditioned. The 2 test groups are then referred to as standard and Tribonex. The Tribonex tapered rollers were triboconditioned in the centrifugal barrel finisher shown in the bottom right. Smooth carbide balls with a diameter of 2 mm were used as the grinding medium. The process fluid that has been used is oil-based and contains tungsten and sulfur. In both test groups, the roughness was measured tactilely and with scattered light. In addition, macro and micro hardness were checked. A possible difference between the micro hardnesses could indicate an increase in residual compressive stresses due to triboconditioning. Finally, the microstructure was examined under an incident light microscope to detect potential grain refinement. Now I would like to present the results of the tactile roughness measurements. The evaluated parameters are Ra, R delta Q, the parameters from the material ratio curve, RPK, RK and RVK, and the skewness RSK. In the upper right figure you can see the selected traversing lengths in blue and the evaluation lengths in red. All tapered rollers were measured along the roller width, on the roller circumference, and on the roller face. Surprisingly, the skewness RSK remains almost unchanged at all measuring points. At the roller width, all examined parameters, except for the reduced peak height RPK, decrease by about 40%. The values each refer to the median. The diagram on the bottom right shows the corresponding box plot results at the roller width. The significant improvement due to triboconditioning is clearly visible. At the roller circumference, no influence of triboconditioning can be determined. That is the direction of the grinding process. At the roller face, RPK remains unchanged. RA, RK and RVK decrease by approximately 25%, and R delta Q decreases by approximately 38%. For the scattered light measurement, the scattered light parameter AQM was evaluated. This parameter represents the mean value from several measured AQ values. In this case, the evaluated measurement direction is the roller width. The table on the right shows the results for the tapered rollers Standard and Tribonex. The parameter AQM decreases by about 35% due to triboconditioning. Tribonex themselves created a scattered light mapping of the 5 tapered rollers before and after triboconditioning. The mapping of one of the tapered rollers is shown on the bottom right. Here you can see the significant improvement towards lower AQ values at the shell surface. Deviations from the results shown in the table are due to different measurement settings. From the tactile and scattered light roughness measurements, it can be concluded that an improvement of frictional properties of the triboconditioned tapered rollers can be expected. This is mainly due to the lower local profile slopes R delta Q and AQM. However, the influence of the process on the surface in grinding direction is limited. Now to the hardness results. Regarding macro hardness, no change was observed due to triboconditioning. Both test groups have a hardness of approximately 60 HRC. Minimal deviations between the test groups are within the range of measurement uncertainty. Triboconditioning slightly increased the micro hardness. This is an increase of 24.3 HV1, which corresponds to a relative increase of 3.2%. Although this deviation is also within the range of measurement uncertainty, the difference could be an indication of increased residual compressive stresses near the surface. But in order to make a reliable statement, the residual compressive stresses would have to be investigated separately. Following the microstructural examination, there was no indication of grain refinement due to triboconditioning. The Standard and Tribonex tapered rollers had a homogeneous martensitic microstructure with iron chromium carbides. To close this presentation, I would like to draw a brief conclusion. I will summarize the presented contents and give an outlook on possible follow-up investigations. The improvement of tribological properties in rolling bearings due to triboconditioning can be divided into 4 points. First, triboconditioning leads to lower boundary friction and a reduction of adhesive wear as well as fatigue damage. This is due to the tribofilm. The smooth surfaces with low profile slopes R delta Q and AQM provide improved lubricant film formation and low running in wear. High wear resistance and resistance against subsurface fatigue damage are achieved by the hard surface with residual compressive stresses down to 10 microns depth. Lastly, potential grain refinement of the boundary layer would result in increased strength, toughness and hardness. Especially secondary contacts in the rolling bearing, such as rib and cage contacts, benefit from the improved friction and wear behavior under insufficient lubrication. Triboconditioning has the potential to replace a superfinishing and burnishing or coating process. An initial investigation on tapered rollers shows the potential of the process regarding surface topography. Further investigations are required to better assess triboconditioning. These are, for example, rolling bearing specific tribo tests, the comparison of triboconditioned rolling bearings with burnished or coated rolling bearings with regard to technical and economic aspects, and a residual stress analysis, for example by means of X-ray diffraction.